All right, first term is 5. So the second term. -2 times a. N is 2. 2 minus 1 plus 14. So what that means, if n is 2, so this is going to be -2 times a sub 1 plus 14. So it's going to work out each time that you're going to take -2 times the previous term. So we're finding the second term. So we're going to multiply -2 by the previous term, which is -5. So we have -2 times -5. Oh, not -5. +5. -2 times 5 plus 14. So that'll be -10 plus 14. And making the next term in the sequence 4. Again, not necessarily when they give you something in recursive like this that it's going to be an arithmetic sequence. So if we want the third term, that means we're going to take -2, multiply it by the previous term, and 14. So we want the third term. -2 times a to the 3 minus 1. So again, that subscript here just means -2 times the second term, because of 3 minus 1, plus 14. So -2 times 4 plus 14. So what we're doing each time is we're just plugging in the previous term to get to the next. Okay. So that's going to be -8 plus 14. So the next term is 6. So then we're going to use 6 to get us the next one. So, the fourth term, -2 times a 4 minus 1. Again, that's the formal notation. All I'm really doing is I'm going to use the previous term to get this. So -2 times the third term, which is the previous one. So that's -12 plus 14, 2. So the next 3 terms in the sequence four, 6, and 2. Again, don't get lost in the a sub n minus 1, because what I'm doing, -2 times the previous term plus 14. Yes.
What's the purpose of the subscript on the -2a?
This one?
Yeah.
That's just telling you you're grabbing the previous term and multiply the -2 by. It's the formal notation. So what it's doing is that you're doing -2 times the previous term. That's why the n minus 1, because that's what it's representing the previous term for that. So again, honestly, with recursive notation, you're just looking for the next term. So if you keep that in mind, and don't get yourself confused with that subscript on it, that can make it easier to look at, okay? So if we look at the next one, find the next three terms, the first five. Yes, you have the formal notation when you're given the recursive formulas. So this right here, we want the previous, we're going to use the previous term. Okay? To get this information. So if we keep that in mind, honestly, I wouldn't worry about doing the a to sub 2 minus 1, any of that mess, because you know you're using the previous one to get to the next. Okay? So we have the first term. I want the second term. So that means I'm going to do negative 3 times the previous term so times 6 plus 20. So I have the now at 6 and I wanted to know what's next. So negative 3 times 6 plus 20. And so the next term is 2. So now I'm going to use 2 to get the third term. So I want the third term. So I'm going to take negative 3 times the previous term plus 20. So that's negative 6 plus 20, which is 14. So far we have 2 and we have 14. So the next term. So I want the fourth. Negative 3 times my previous term, which is 14, plus 20. So, you don't have plus 20 on your sheet. You don't. You don't have plus 20 on your sheet. Is it a 3, negative 3 times a7, and no plus 1?
You skipped.
Oh, I skipped to number 2.
Yeah.
Okay, well, it's okay. Let's keep doing this. We'll jump back to the other one. Sorry. It's like, wait a minute, this doesn't look right. All right. So, negative 3 times 14 should be negative 42. So there's the next 3. Find, we want the first 5. So give me 2 more. So again, use the, actually 1 more. Sorry, we've already got the first term. So I just need the 5th term. I'll go back up and we'll grab one here. So the 5th term will be negative 3 times the last one we just got, So that's a positive 66 plus 20 gives me 86. So the first 5 terms of the sequence. Six, 2, 14, negative 22, and 86. Again, recursive notation works when it's not necessarily a geometric or arithmetic sequence, but it gets very tedious because you have no way to go through and find, other than just continuing out the sequence, to get something further down the line. Okay. So let's jump back to 1. There we go. We have the first term. We need to start looking for the second. So the second term is 3 times the first term, the previous term. So that would be a negative 12. So the third term is 3 times the previous term. So that makes it negative 36. Find the next 2. So again, these are sequences with recursive notation. Here's what we have now. What's next? And that's what allows us to get. All right. So the fourth term, 3 times the previous term, would be a negative 108. And the fifth term would be 3 times the previous term, which would be negative 324. So then we list the first 5 terms of the sequence. We start with the negative 4 that they gave us for the first term, negative 12, negative 36, negative 108, and negative 324. So recursive, not necessarily the easiest to use. All right, see what you can do with this one. Find the first 5. They gave you the first term. That's going to go here to find the second. So your second term, 0.5 times the previous plus 8. And then you'll keep doing that to find the next 4. 0.5 times the previous plus 8. So we've got half of 64. So that's the fun part about being up front, is you get to talking and let's see, 20 plus 8. And as you're explaining things and going through things, you're not exactly saying what you're writing, because you're doing 2 different things at once. That's always where it gets fun. All right, we good now? All right. So the fourth term, 0.5 times 28 plus 8. So 14 plus 8 is 22. And the fifth term, so we have 11 plus 8. How do you do? Good? Better? All right. So the first 5 terms. Are 64, 40, 28, 22, 19. Okay. So, recursive notation only allows you to get from where you were previous to the next. Where you're at now, just get to the very next term. That's all it's going to allow you to do. So, when we look at writing a recursive formula for a specific geometric or arithmetic sequence, first of all, we got to decide which kind of a sequence we're doing. So on this one, I have an idea because that's a pretty drastic change from 216 to 36 to 6. But we also can just check the math on it. (216 minus 36). Let's see. 180. And then 36 minus 6, clearly not arithmetic because we're not using the same value to get to the next. So it's geometric. Again, we can double check. 36 over 216 because we do need what that is. So that should be 1/6. We double check. 6 over 36, 1/6. Again, remember your common ratio is the next term over its previous to get the common ratio. So it's geometric. The common ratio, which we will need, is 1/6. So, we're going to use the formula. Okay. So all we're doing is writing the formulas. We're not doing anything. So this is a recursive formula. So again, all this is going to be able to give us, in this specific geometric sequence, if we have a term, we can get to the very next one. Explicit formulas, those are the ones that allow you to get to any term in the sequence that you want at any time. So we want geometric. So writing this, the whole formula that you need, okay, is a sub 1. If you're writing a recursive formula, you have to know what the first term in the sequence is. Then we're going to write a sub n in our 1/6. And again, this a sub n minus 1 that just means the previous term so that you can get to the next one. Okay? And that just indicates that they gave us the first term, so we're going to be able to start finding the second term. That n is greater than or equal to 2. So even on an arithmetic sequence, if you're writing the recursive formula, what the first term is, the formula with the common ratio in it, and allowing you to find now the second term, and then on from there. Okay? So, I'm going to check arithmetic first. We're adding a -6, adding a -6, adding a -6. So we're good to go. That is an arithmetic. And that formula is whatever the previous term is plus the common difference. So previous term plus the common difference. So, here we go. The first term in the sequence is 22. And now I just put in the common difference. So you can either do plus a -6, or you can write it as -6. Either one of those is acceptable. Okay. Good. See if you can write the next two. One's geometric, one's arithmetic. Okay, so let's look through. That's jumping pretty drastically. From 5 to 15, 15 to 45, that's jumping pretty drastically. So I'm going to go on ahead and test for the geometric sequence. All right, so each of those equal 3. So we have a geometric sequence. Which means we are going to use the formula. We're going to use common ratio times the previous term to get to the next, which is exactly what you did when you were looking at geometric sequences. You multiplied the previous one. If I wanted the next 3 terms in the sequence, I'd multiply 135 by 3, then by 3 again, then by 3 again. So this is just giving you a formula notation for doing this. So, the first term is 5. The formula, 3 times the previous term. And that it'll allow us to find the second term and on. So if we take a look at 6, we're adding 17 to get to the next one. So that would make it arithmetic. So that would be our a sub n, the previous term, plus the common difference. So we start with, first term in the sequence is -3. We get to the next term by adding 17, and that allows us to find the second and any term after that. So this is putting a formal formula to specific arithmetic and geometric sequences. Now the first ones we did, they weren't either. So that was just where we're at now and just what do you do to get to the next one. All right, last couple things. Explicit formula versus recursive. Explicit formula allows you to find any term you want in the sequence. Recursive formulas only allow you to find the next one. That's the difference between the two. So, for each recursive formula, write an explicit. For each explicit, write a recursive. So that is clearly an explicit formula. I don't see a sub n minus 1 or anything in there. So to write a recursive formula, I need the first term. So that means the first term is 7 times 1 minus 10. Which is -3. So the common difference is right here. Sort of. So that rate of change, the slope in the linear equation, that's your common difference. So the first term is -3. We get to each term by adding 7. So to go to the explicit formula, all you have to do is find the first term. Everything else you need is there. Because that common difference and a linear is that rate of change there. Okay. So first of all, we have a geometric sequence. And its explicit formula, double check, is this. First term times r to the n minus 1. So do I have the first term here? Yeah. And I clearly have r. You can put them. You can do it that way, or put parentheses around it. Any of that works. So here, we went from only being able to find just what the next term is to being able to find any term in the sequence. Okay? So that's your difference with these two.